each component. And then when you add, you just add all the x components and the y components separately. And that's how it works out. So that's number 5. Let's take a look at number 7. So now we're given, yeah, that's what it looks like. 5 probably got switched out. I think I added, that's what I did. I added a couple more problems there, but I didn't switch it around appropriately. Okay, so that's number 5. Let's take a look at number 7. That has some different sort of vectors, but now we're using the ij representation as opposed to these what they call brackets notation over here. I think for 7 and 9 we're using the same thing. So now we have vector u is equal to minus 2i plus 3j. And v is 3i minus j. Now, you could also put, like I'm putting a regular vector. I put a hat vector because these i's and j's are just unit vectors. And w is 5i plus 4j. And I think that's it. And t is minus I minus 6j. Okay, so now for number 7, we want to look at the following. For 7, it's just u minus v. So vector u minus vector v. Let's put that in. So I'm taking my u, which is a minus 2 in the I plus a 3 in the j. And I'm subtracting v, which is 3 in the I minus 1 in the j. So I'm going to drop the first pair of parentheses over here. So it's minus 2i plus 3j. This negative gets distributed just like in regular algebra class. So I can drop the parentheses here. And then I end up with minus 3 in the I plus 1 in the j. Now, how do I combine these? Well, you combine the I and the j components separately. So the i's combine together, and then the j's combine together as well. So in this case, I would have a negative 2 plus a negative 3 in the I would give me a negative 5 in the I direction. And then over here, I have 3 in the j plus 1 in the j gives me plus 4 in the j. And that would be my answer to vector u subtracting vector v. Okay. So these are just like my, if I wrote, you could also write this as minus 2 comma 3 in the other vector form. And this is 3 comma negative 1. If I wrote it in the bracket form rather than the ij form. That's just another way of expressing something that has direction. We need these two different components to give us direction and a magnitude by taking, like the Pythagorean theorem. This is the, the length along the diagonal. Okay, so that's number 7. Let's take a look at number 9. It also uses the same vectors there, and it says, take a look at the magnitude of the vector w. Think of it this way. This is a way of viewing it. I'll show you the formula for doing it, but you can think of this vector w. This is one way of visualizing so you see what's happening. This is the I direction, which goes along the x-axis, and that's the j direction. This is 5 in the I, and we go up here, 4 in the j. So this vector is right here. So over here, that's the height of 4. And over here, that's a length over here of 5. We're looking for the magnitude. That's what this is. How long is that vector? That's what we call the magnitude of the vector w, its length. So we have what you see right here is a little right triangle. 5, 4, and we'll call this, say, D right now. which is nothing more than the magnitude, the length of that side. And it's a right triangle, so I have Pythagorean identity. D squared is a squared plus b squared, which is 25 plus 16. So d squared, magnitude squared, is equal to 41. So d, over here, if I'm looking at this, d is just equal to the square root of 41, and that's the length of w. That's the square root of 41. So all of it is simple right triangle. Now, how do you write this in general? Well, if you want to write this in general, then the magnitude of w, by using a formula, is you take its x component, whatever that might be, and you square it. So over here it would be the square root of my 5 squared plus 4 squared. Now, actually, when you get into more with vectors, it involves something that we're not going to do here called the dot product. So there's a lot more on vectors. We're just doing addition and subtraction and the length of a vector. There's different types of ways of multiplying a vector. There's actually 4 ways. There's a scalar product, there's a dot product, there's a cross product, and there's what they call an outer product. Don't use the outer product too much. That will create things that you've heard in Einstein's theory of relativity called tensors. And they're also used a lot in mechanics and stuff like that, continuum mechanics. But that's just, how long is that vector? If I draw the vector, it's that length, Pythagorean theorem guides me. But there's another way of writing this as, w dotted in with itself square rooted. But that's going to come later on. You don't need to know that just yet. But they'll start to expand upon this. That's why I want you to have a basic idea of vectors, so when you start adding in the new stuff, you're not learning everything at once. You're just learning the new stuff. You have some foundation for this more basic stuff as well. So 7 and 9 and 11 is also in the same group. Okay, so let's take a look at problem number 11 here. And what do they want? So it's u plus 2v, u plus 2v minus 3w plus 2t. Minus 3w plus 2t. Okay, I'll set the same thing up. So it's minus 2I plus 3j plus 2, but parentheses, 3I minus j minus 3 parentheses w is 5I plus 4j plus 2, and t in this case is just minus I minus 6j. Let's distribute the 2, negative 3, and the 2. So I'm just going to distribute each of those. At a time. First one doesn't change. It just stays as a minus 2 in the I plus 3 in the j. This then gives me 2 times 6 gives me plus 2 times 3 is 6 in the I. 2 times minus 1 is minus 2 in the j. I'm going to distribute them negative 3. Negative 3 times 5 gives me negative 15 in the I. Negative 12 in the j. 2 times negative 1 is negative 2 in the I, and negative 12 in the j. So now what do? Well, I need to combine the like parts of these vectors. So I'm going to put all the i's together. It's kind of like doing like terms, if you will. Those will combine together, and I will also be able to combine the j terms together. So for the I terms, what do I have? I have a minus 2 plus 6 minus 15 minus 2. This is all in the I direction. Plus now if I look at the j, I have 3, subtracting 2, subtracting 12, subtracting 12 again, and that's in the j direction. Now just do some arithmetic. That's 4. 4 subtracting 15 is negative 11. Subtracting 2 gives me a negative 13 in the I direction. Plus over here, so 3 subtracting 2 is 1. Minus 11 minus 12 gives me a negative 23 in the j, which oftentimes we won't write it as adding a negative. We'll just write that as minus 13i minus 23j. Let's see if is that one correct or not? I'll make sure I double check these. That's number 11. So nope, another typo there as well. So I got to go through those. This is 13. I don't want to wrote the other one, but I want to write 13. I'm talking and writing at the same time, so made a little sort of mistake there. So it should be 13, just like that is there. Didn't copy it correctly there. Minus 13 minus 23. Okay, the other one's 7. I'll double check those as well. For 9, we got 25 and 16, we got 41. See, these are all messed up. I think I changed these around dramatically. Yeah, so I apologize for that. Yep. So that's it. You probably got it correct, but now you can see exactly what is what there. Make sure I got everything there too. Right. Make sure I didn't miscopy something there. Double check on that. U plus 2v minus 3w. Right, plus 2t. Yep. So that's correct. Okay, so that's the correct answer right here, right down here. Any questions on that now? Is that okay? Getting a little bit better now? There's some typos in the answer key there. So that's doing some basic arithmetic. Multiplying, vectors by a constant and then adding or subtracting multiples of vectors from each other, as well as finding the magnitude of that direction, how long that vector is. You're going to be looking at other things to find its direction. And again, you're going to be just using some basic trig that we developed early in the course. Now, if those of you that go on to Calculus 3, that is called vector calculus. And those of you that have to take a course in engineering and statics, you're going to deal a lot with vectors there. Statics means you take forces, you're going to let things, sit, like bridges and things, and then we have some I-beams there that kind of illustrate the very introductory version of that. We have to, anything is static, it's not moving, but the forces are acting on a body that's not in motion. So you have to balance all the forces. Since it's not moving, forces up and down cancel, and forces left and right cancel. Horizontal and vertical forces must cancel. And that's what the last part is. Okay, so that leaves us number 13, because somebody wanted to look at that problem that I've been alluding to right here. So I think we're done with those vectors. Let's go through and check those and get those correct. So let's take a look at another application of these vectors. This is the first very basic application that you will get. You're going to be using, if you continue on in any level of mathematics beyond this, you'll be using vectors quite extensively. So in problem number 13, we have a graph. We have like an I-beam over here. And then we're hanging a weight over here. From that I-beam, and it has two little eye hooks over here, one over here and one over here. And we have some metal if you will, cables, if you will. And this has a 1,500-pound weight on it. And there's tension in this cable. We'll call that T1, magnitude of a tension. And there's tension in this cable, T2. How much force is pulling on those cables. And they've given us some information about the angles here. So this is 65 degrees, and that is 30 degrees. Now, this is what we call a static equilibrium problem. We have a force that's pulling this down. So we have a downward force due to gravity, and it's putting tension in these rods. You want to make, or these cables. You want to make sure that the cables can withstand whatever tension is there. They do that a lot in bridges and trusses, and they want to make sure that the forces that act on those things are not going to snap those cables. So they have to over-design it. You don't want to just barely design it so it's the kind of the minimal amount. You want to make sure it can withstand the range of those forces. This is what we call a static equilibrium problem. Meaning it's static, so there's no motion. This thing is not swinging. It's not dynamic. It's not dynamic motion. It is static motion. Or static, which is not motion. So what do? Well, what we do is we kind of take the important parts over here, and the static equilibrium, what they require is that the sum of all the vector forces, because it's force vectors that are acting on it, because a force has both a magnitude, how much of it, and in which direction. Sum of all the vector forces must equal 0. That means it's not in motion. If there was an imbalance, then it would move. If there was a greater force in one, either up or down or left or right, it would move in that direction until it balanced itself out. So this requires two things. This requires that the sum of all the vertical forces is 0. This is the requirement. And the sum of all the horizontal forces. So any forces that go this way have to balance out to give you your net sum is 0. And the sum of all the horizontal forces is also 0. So summing forces this way have a net force of 0. Okay, so let's take this and create a picture to kind of deal with. So I'm going to, if I wanted to, I could simply, let me do it right beneath it, and then I'll place it over here. So I have this over here. Now, these are the important pieces I have. I have this, and I have this. Oops, put it over here. And I have that over here. And I have this force that's going downward over here of 1,500 pounds. I have this angle over here is 30 degrees, and this angle over here is 65 degrees. What we're going to do is we're going to establish a reference side to create our angle. This is going to be our reference line in which we can get all the angles. If this is 30 degrees, then we have angles. If these are two parallel lines, that's parallel to that line. This then becomes 30 degrees here. If this is 65 degrees here, this becomes 65 degrees here. Okay. Now let me kind of erase that picture and kind of deconstruct this and put this over there and see about how do we sum horizontal and vertical forces. We're going to put the tensions. I'll put them here over here. This is what we call T2, and that's T1. So what we're dealing with here in vector form, it looks something like this. So we have this point here. And this goes down a vector, and it's 1,500 pounds. Then we have another vector here that's kind of going in this upwards direction. It's pulling it upwards, holding it upwards in that direction. And another vector over here that's holding it upwards in that direction. Now, I'm not making these vectors the length of the forces. We're just kind of doing it arbitrarily. And I could call this, if you wanted to, this is kind of like vector T2. And here's a vector T1. And here's my reference angle. This over here is 30 degrees. Now, what I also need is, this angle here is 65 degrees. So since this is my reference side, I'm going to reference all my angles from this. I go from here to here. That angle is essentially this red angle plus 65 has to add up to 180 degrees. So this angle here is 180 degrees minus 65 degrees. So if I go from here to here, that's 180, but I'm subtracting off 65. That gives me, in this case, 115 degrees. So that's this angle here in red. Does everyone kind of see that? Because we set everything up by the references. Okay, now let's look at the sum of all the vertical forces. So what we're going to do is we're going to construct some right triangles over here and use our trigonometry. I can drop this down over here, make a right triangle, and over here I can make a right triangle. So let's sum all the, vector forces in the vertical. Now, what we could do is kind of look at this, because this vector here, let's say I looked at this vector here, right here. Take a look at this one. I'll look at it in separate. So put a little circle around this guy here. So I have this vector here. And I'll just call that vector t sub 2 for now. Vector t sub 2 has two parts. It has a vertical component. This is my reference side. So if I project downward, it has a vertical component right here. Okay, that's a vector in that direction, but it also has a vector in that, which matches that line there. The magnitude of this vector here is just its length. Its angle over here, this is some angle here, we'll call that, and now I'm just going to call it theta, but theta is 30 degrees in here. I can move that over, and you see you have your right triangle again. So vector t has two components, so t2. Now, remember, what is this? This length over here is the length of this times the cosine of theta. So remember from our basic trig, our right triangle trigonometry over here, that down here, this thing here is the magnitude, the length of that vector t2 times the cosine of the angle theta. That's that one. And it's going to be in, I'm just going to write it in the I direction, in the horizontal direction. The magnitude of this vector over here, well, it's pointing upwards. So I start with the magnitude of t2. But that component is in the sine of theta direction, a sine of theta magnitude in the j direction. So I have a vector that has a horizontal and a vertical component. Okay. I can also do this other kind of triangle over here and kind of draw that underneath it just so you show. Then we'll see the easy way of looking at it. So now again, we still have our reference line. Now we have this going this direction, a little bit higher up. And I could then construct, if you will, Well, this angle here, let me put it up there, is 115 degrees. And this over here we know is 65 degrees. Now we could figure out these other angles as we desire over here as well. So let's bring that vertical down over here. That's 90. The sum of the interior angles of any triangle are 180. If we wanted to, we could put this as 25 degrees, just as I could put this as 30. So that's, you know, if that's 30, that would be at my 60 degrees. So this is going to be theta is 30 degrees and 30 degrees for that particular problem. Okay, so we can also put the tension of vector over here. So it's going in that direction. That's vector T1. I have over here T1. Okay, so that also can be broken down into both a, if you will, it's horizontal and vertical components. So this over here, you can see we are pointing in this direction. And for that, all we take a look at that is equal to the, if you will, the sine of the tension magnitude times the sine of 65 degrees, or the other theta over here. So over here on this side, that's the magnitude of T1 times the sine, because that's the sine of that angle, will give us over here of, 65 degrees. And that's going to be in the J direction, the vertical positive J direction. Now over here, we could either use the cosine of 115 degrees to get it to go into the negative, or I can use minus. Since it's going in the negative x direction, what I could do is I could put minus the magnitude of T1 times, if I wanted to here, just write that as the cosine of 65 degrees. Or I could also just say it's the magnitude of T1 times the cosine of 115 degrees. That would still get, that would turn this into a negative value. And then finally, I have this one over here. Let's just put that over here in its vector component form. Get all these different colors and everything over here. This right here going right down, that only goes in the J direction. So that is just equal to a negative 1500. That's the magnitude in the J direction. Okay, horizontal forces are in the I, vertical forces are in the J. So let's set everything up. Let's start with the, doesn't matter. Let's start with, if you will, the vertical forces. So if I could have in the textbook, vertical. So what I have over here, both of these are pointing upwards, these components. So I have this one, the magnitude of T2 times the sine of 30 degrees, that's in the J. Here's another one in the J, plus the magnitude of T1, and that's the sine of 65 in the J. I'm not putting the J because I'm just putting all the J's together. These are all the J's. Has to balance out this force over here. So that has to equal to 1,500 pounds. And these are all the verticals. That means the J's. Putting all the J's together. So I put it on the, if I put it on this side, then it would be a negative. But if I put it on the other side, it's positive. So if I put it over here, it's negative. Those would have to be 0. They would balance each other out because it's negative here, okay? But then I just moved it to the other side and it becomes a positive on the other side of the equation. But with those forces, it would be negative, like it's here, and it would cancel everything out. So this is one equation that I have by summing all the vertical forces. Now I have to sum the horizontal forces. So the only thing I have is I have this one and this one. This is not giving any horizontal forces. So for that one, I simply have the magnitude of, doesn't matter, let's start with T2. So I take the magnitude of T2 times the cosine of 30 degrees. Now, if I choose plus, then I'm going to use 115 degrees. If I choose minus, I can use the 65. It doesn't matter. So I'll do plus. Plus the magnitude of T1 times the cosine of 115 degrees. That must equal 0. There's no counterbalance over here. Now again, as I said, I could have replaced this with minus the cosine of 65 degrees if I wanted to. And then that would turn that into a negative. They'd be canceling each other out. So what I have, what are my unknowns? Gets complicated. I don't know the magnitudes. What I wanted in the very beginning was the magnitude of that, we call that T2, at tension in cable 2 is nothing more than the magnitude of vector T2. That's an unknown. The tension in cable 1 is nothing more than the magnitude of that vector T sub 1. And that's the tension. So both of those are my unknowns. This is like an X and that's a Y. And I want to solve this equation. So I have a system of two equations that I would like to solve. So now we just go through and solve the system over here. So what I can do, I can solve this equation here for, I don't know, say T1 and substitute it to the other one. So taking this is equation 1, there's equation 2. Take equation 2 and solve for T sub 1. So what do? So I move the T sub 2 over, so it's equal to a minus T sub 2 cosine 30 degrees over, when I move this over, I then divide by the cosine of 115 degrees. So there's my T sub 1 in terms of T sub 2. And what do I do with this? I now come over and replace this into equation 1. So now for my T sub 1, I'm going to replace it with this. So I have for equation 1, I have T sub 2 in magnitude, sine of 30 degrees. This is where I'm going to actually replace it. So we'll do it in a different color so we can kind of see what we're replacing it with. So I have my plus T sub 1, I'm now replacing with minus the T sub 2 cosine of 30 degrees over cosine of 115 degrees. And all that has to equal, that's my T sub 2 times the sine of 65. So here's my T1. This is all T1. Then I get another sine of 65 over here. And all of this has to equal 1,500. We'll drop the pounds for now, drop the units and come up with those. I have a common factor of T sub 2 that I can pull out. So T sub 2. And then over here, I have the sine of 30 degrees minus cosine 30 degrees, sine 65 degrees, because I'm getting rid of all this, cosine of 115 degrees. All that is equal to 1,500. I want to solve for this T sub 2, so I simply divide by that. So I get my magnitude in tension in cable 2 is equal to 1,500 over this expression here. Sine 30 minus cosine 30 sine 65 over cosine 115 degrees. Plug this into a calculator. Let's see what we get. And that's going to give us some magnitude. And then once we have T sub 2, we plug it right in here and we get T sub 1. Let's see if we got that right or not. Plug it into my calculator. We're running out of time here, so I'll just run it quickly. So I'll take my 1500, and I think I am still set. Let me just double check. Always check your mode over here. Yeah, I'm still set for degrees from the other day. 1500 divided by sine of 30 minus cosine of 30 times the sine of 65 divided by the sine of cosine of 115. So I get, in this case, 636.35 pounds approximately. Now it's approximately 636.35 in my units of pounds. Now I can use that in here. So I have this value here, I have T sub 2. Take this T sub 2 I just got here and substitute this for T sub 2 over here. That's going to give me my T sub 1. So I take that value, multiply it by the cosine of 30. I'm going to take that times the cosine of 30 and divide that by the cosine of 115. And I get, with the negative out front, this turns out to be 1,304 pounds. So I get my, using this over here, that tells me the magnitude, the tension T sub 1 is approximately equal to 1,304 pounds. And that's how you find it. It's complicated. That's why a lot of students do not do well in statics courses. It's so easy to make mistakes and to mix things up and not get the correct answer. And that's essentially what we have. You could round this in the textbook and round it to 636.4. So that's how it is. So you're summing the vertical, and I forgot to write it here, you're summing the horizontal. These are the horizontal forces. Sum the vertical, sum the horizontal. You break it all down. So you can see, if you have to take a course in engineering statics or something, or physics, this is what you're going to deal with. A lot of the trig we developed early on, and that's analytic trigonometry. Okay, so we're out of time, but hopefully you go through that again if you're still having difficulties. There's some other ones in the textbook to kind of give you that, but hopefully that helped a little bit. And you see how I broke it down, because I did it all step by step. And it's also about just balancing the vertical and the horizontal. I like to treat it, like I say, with the I's and the J's. That's a little bit easier to set this up rather than using the bracket notation. So this is where it's ideal to use the I and the J notation to see how everything works together. Now, if you get a negative when you're expecting a positive, you're probably using the wrong angle. You're probably using cosine of 65 degrees. And you should have introduced a negative into your things over here. Because I could have, like I said, over here, wrote this cosine 65, but then I would have had a negative over here, and that would have made everything. That would have cosine 65, that would have been positive. I would have gotten the same result. Give me the same answer. Okay, so smile, wake up, stay safe, have a good weekend. If you still have questions, we can go over another one on Monday. We have a little bit of time there, but we're going to be moving on into chapter 11 now. This is the graphical analysis. It's kind of like everything taken together. All the stuff we've learned, try to use different aspects of it to understand graphs of functions. And that's really critical in the calculus, because that's what we do. We develop new tools in the calculus to analyze graphs of functions. In addition to just finding where they cross the X and Y axis, the intercepts, and a few things like that. The domain and range, we look at things such as intervals of increasing, decreasing, maximum, minimums, absolute max, absolute mins, and we do all these extra tools to analyze them. So any questions? before we wrap it up? Okay, sorry if I keep you a little extra longer.